Let's go to the simplest example of a GLM, which is just rehashing the linear model, which is of course an example of GLM, but as are other things. So assume that the data are normal and that yi is the means. I'm going to use the specific notation that expected value yi is mu I, and then our variance right there, and they're going to be independent. And it turns out that the Gaussian distribution is an exponential family distribution. So I'm going to define the linear predictor to be this. The linear predictor is always going to be that. It's going to be the kind of systematic component that relates the sort of I parameters. It reduces it down to p parameters via the covariates, the x's. Okay. So that's the linear predictor. And in our case, we have this link function, g of mu, that's g of mu equal to eta. And so this is always the case. The link function is such that it links the mean of the y's to the linear predictor. That's why it's called the linear the link function. And in the linear models, g of mu is just mu, so that mu I and eta I are the same. So in other words, the mean satisfies this relationship, and then we're just back at the ordinary linear model that we all know and love. So this yields the same kind of likelihood as our just ordinary additive Gaussian linear model. Okay, let's do so-called logistic regression. Assume that our outcome is Bernoulli with success probability mu I, so that in this case expected value yi equals mu I, and 0 has to be less than or equal to our mu values, which have to be less than or equal to 1. I'm going to define my linear predictor right now as eta. So linear predictor meaning it looks just like the regression model. It looks just like our regression model, though it's not added to the response isn't it plus error. So this function here, g of mu, in this case, is the function that links the mean of the y's, mu, to the linear predictor eta. And in logistic regression, that function is the log odds, log of mu over 1 minus mu. So just to remind everyone, hopefully everyone's had the inference class so that they can see, or they can recall that if you take a probability and you divide it by 1 minus the probability, that's called the odds. And so in this case, the logit is the logit is equal to the log of the odds. It's a particularly nice function. We can invert the logit, the kind of so-called inverse logit. If eta is equal to log mu over 1 minus mu, if we invert it, here I added the I. If we invert it, we get this expression that mu is x above eta I over 1 plus x above eta I. So if we were to take these means and well, forget about taking the means right now. Let's just write out the likelihood for all of the mu's, right? And so this is just you remember the Bernoulli likelihood is mu I to the yi 1 minus mu I to the 1 minus yi. And I think maybe you remember it probably more as something like we did pi to the yi 1 minus pi to the 1 minus yi, but we've just relabeled p as mu. Okay, so and then we take a product in front of it because that there are a bunch of independent observations and the likelihood takes the product. Okay. So if we take this likelihood and then plug in this expression into it, and then this is the expression for 1 minus mu I, then you can reduce it down to this, that the likelihood looks something like that. And fitting this, obtaining, and then we could further plug in for the eta i's, we could further plug in the linear the summation of the xi times beta. We do that here and there, and then you see the likelihood that gets maximized in order to fit a GLM. It's no more complicated than that. Let's do a Poisson example. So now our y's are Poisson mu I, so that expected value of y is mu I, and that's not true. I'll get rid of that in the slides. Where mu I has to be greater than or equal to 0 in the Poisson case, but it's unbounded on the upper side. The linear predictor is that guy, right? And the link function, let's say in this case, is log mu. Okay, and then remember that e to the x is the inverse of log x. So if a to I equals log mu I, then we can turn around and invert it and write it that mu I equals e to the a to I. So if we write out the Poisson log likelihood and simply plug in, for our mu's, plug in e to the a to I, and then we wind up with an expression that looks something like this.